And this is connected. We're no longer restricted to time-independent Schrodinger equations. Probability constant. So first thing I'd like to remind you is that there is a probabilistic interpretation for the wave function. So I can define a probability density. Let's say, this is general enough. Let's say in 3 dimensions. Okay. All right. There's a probability density, which is defined as the magnitude square of the wave function. And the probability density is connected to the interpretation of the wave function. So now I ask the question: how does for in general a time-dependent wave function, how does the probability density evolve with time? So take its partial time derivative. Right? This amounts to now you see, okay, where do we go from here? You see the time derivative of the wave function. So we can relate this to Schrodinger equation. So write down the Schrodinger equation. This is h phi is equal to okay. So now if I take this complex conjugate, the Hamiltonian is unchanged because it's Hermitian. Okay, now if I move these factors of IH bar across, then I can substitute for the time derivatives. Okay, so let's do that. So for this one, I will have 1 over IH bar H phi, and this one I will have minus 1. So let's plug these in. Hello. So what is the explicit form of the Hamiltonian in general in 3 dimensions? It looks like there's the Laplacian in here, okay? And then you add in whatever potential function you have. So let's write this out explicitly. And you can see that because of this minus sign, and this plus sign over here, okay? And well, I'm just simply doing multiplications of the potential function with either of these wave functions. They must cancel out because I'm free to move the wave function across. But that's not the case for this. You can't just move a function across this Laplacian operator. So we get that, and there's a minus sign here. These terms can be combined. Combine them into, let's put the I on top and reverse the order here. Okay.
Did you explain why the V disappeared?
The V disappeared because phi V phi conjugate is equal to phi conjugate C phi. Okay. Because I can move them across. This V is just a function. It's a simple multiplication, not an operator, not an operator. So, where was I? Okay.
Or, I mean, it is an operator, but it's just that it's a commutative operator.
But the wave function is not an operator.
No, it's with the V.
So V,
It's a community function.
you can't, because when you move across, when you move two operators, that's you can say the community one. But when you try to move away from the cross an operator, that doesn't have to do with it.
When you think of V as a diagonal operator, then that contradiction of V is the diagonal matrix.
Because, for instance, your V could very well contain operators that doesn't commute with, say, your position operator or something. But the thing is, we have already written everything in the coordinate representation, and these are just simple functions in here. And so moving functions across is always wrong. But these are operators on functions. Okay, and then let's treat this term. Now, I can treat this term by introducing the divergence, okay? Because we can check that. If you carry this divergence out, or you will have the gradient of phi conjugate from here, minus the gradient of phi conjugate and the gradient of phi. Again, two functions, they're the same, they cancel. And then the other one would be just this. Okay. So I can factor out the divergence operator. Okay. So now I have written it in a form like this. And when we're talking about current and conservation laws, we typically think about something called the current conservation or charge conservation. So in analogy, we have this in electromagnetics. Okay? So now you notice you have factored out a divergence operator. Okay? So over here, why don't I group everything else together? Okay? So I can define a probability current by as this. Okay. So this has the physical meaning of. Now this is both a function of x and t, right? Of position and time. This has the physical meaning of how much of the probability is flowing across that point at a certain time, or flowing across a certain surface. If you integrate this across some surface, this is the current density.
You may want to remind us of the chain rule for the divergence operator in order to go from the third class line to the second class line. Divergence of scalar and the vector.
This is a scalar. This is a vector because of the gradient of a scalar function. Okay. So if I have a scalar function multiplying a vector function and I take the divergence of it, right? So now, first of all, getting your head straight. What is going to be the resulting answer? It's going to be a scalar. So first thing is the gradient of this dotted with that vector. Okay, it's a scalar, no problem. Okay, and then the second thing is this multiplying the divergence of the vector. So still a scalar. So the first sanity check is to think about whether this is a scalar or a vector. So this applies here.
Yeah, but then actually you also have to mention that some terms cancel. Right? As I apply the chain rule, sometimes some intermediate
Okay, let me carry this
cancel
out
and then
explicitly. Okay, so when I do this, I get this term plus this term, right? So now when I write down its complex conjugate, which is this, I get this term and this term. Okay. Now I subtract them. Okay. So obviously this and this cancels, right? So you're left with this minus this, which is this term. Okay, this is equal to this. Okay. So this is the probability current. And the important thing about the probability current is that it allows us to study scattering states.
You want to indicate J as the factor. J is actually-
Yeah, that's right. J is a vector. Okay. Okay. So remember, we defined what a scattering state is, right? It's when you will have scattering states when the energy of the wave or the particle exceeds the energy at either side. Okay. So for instance, we could consider the potential step. In one dimension. Okay. And then let's say that there's a step at x equals to 0. And the strength of this step is V naught. Okay. So we're going to study a scattering state on both sides. So meaning that we have a wave incident on this potential, and its energy is above V naught. So okay. So let me draw a little illustration. Energy of the wave is here, and it's incident on this potential. Okay. So, because we say there are no incident wave on the other side, right? So on this side, when we guess for the general form of the solution, there's only going to be a right flowing wave. Okay. So I guess for this, I'm going to write, and this is a transmitted wave, so let me use T. And transmitting from the left side, okay, TL. And then on this side, you have K, okay, on this side you have K equals to M on this side, let's use Q again. Okay, now you need to get the factors. When do I take V minus E? What do I? It all has to do with if you're taking traveling waves, you want to make Q a real number, and then you want to write the I on the x, or x greater than or equal. Okay, and then let's consider a wave incident with unit amplitude. Okay. So the incident wave on the left side is this, and there will be, of course, a reflected wave. And let me say reflected when it's incident on the left. Reflected wave. And it looks like this, or x is
sorry, could you move to the right? Yeah.
correct. Sorry. Okay. So are there any questions as to the form of this?
Yeah, the scattering state has nothing to do with the probability current.
Not yet, but we're going to. So basically, we want to find out how much does it transmit, how much does it reflect, and the way to define these things, you need the current, how much current goes through, how much current goes back. Okay. So where was I? Okay. So now you do the same thing, right? Match boundary conditions at this point of discontinuity. Okay. So 1 plus RL match boundary condition as x equals to 0. Okay. Is equal to 2L, and then you also have the first derivative, right? So I K 1 minus RL is equal to I Right. Okay. So I want to I want to represent the transmission and the reflection coefficients by K and Q, which are known quantities once I specify the energy. Okay. So you have no doubt seen this before. detailed definition in the notes. Yeah, that's true. Okay, you get these by rearranging some terms up here. Right. So now I want to, using the concept of probability current, to see that we want to investigate what happens to the what is the ratio between the incident current, okay, the reflected current, and also the transmitted current. Okay. So now, because this is the incident wave, this is the reflected wave, and this is the transmitted wave. Right. So what we do is we just plug these things into this expression. So because they're so simple, it turns out this is just h bar over 2m. Okay. And this is just RL. I believe it would be magnitude squared. And then this is just alright. So now I want to investigate the ratio of the current that was incident with the ratio of the current that was reflected. Okay, and because this reflected current, of course, remember this is a vector. So in one dimension it's going to become having either sign. And of course reflected current will of course go that way. So rigorously we should take the magnitude here. But there might be a minus. Okay, so now this is simply given by RL squared, which explicitly is k minus q k plus q squared. And then we want to write this in terms of the energy and the and V naught. Okay, and that turns out after some simplification. Let's try to make sense of this. Now, when does the reflection coefficient becomes unity? That's when the energy is the same as V. I actually use V naught, sorry. Okay, so when the energy is the same as V naught, the reflection becomes unity. Okay? Nothing gets transmitted. And in the case when E is much greater than V, okay, we can find out what this is. Okay, so let's say that V over E goes to a really small quantity called epsilon. Okay, so that means in this limit, 1 minus okay, so how do we treat the square root when it's a really small quantity? It's about a half. Right? So 1 minus 1. Okay, and then there are some cancellation. We get a half epsilon.
I think you just work out one of the JIs. You know, JI, JR,
Oh,
AC
okay.
being one of them, and you say it's very easy, but just work out one of them.
Well, let's work out JR. Because there's a sign ambiguity here. Phi R is equal to RL minus phi kx. Okay, so JR defined as. Alright, so we write down phi now the gradient turns into ddx. So ddx of the conjugate, so phi r conjugate is equal to, we don't know if the RL is real or not. Okay, so in general it's going to be complex. Okay. Now we take its derivative, you get a ik here. RL conjugate dx. Right? And you see how there's a minus sign because of the 2i's. And now minus okay. Now the 2 minus sign turns into a plus sign, and I can factor out the ik now. And what's left is 2 times RL magnitude squared. So it's minus h1 over m squared. Is that correct? Okay. Is everybody okay with this? Alright. So let me get back to extracting the asymptotic behavior here. Okay. This is approximately, because epsilon is really small, okay? This is approximately epsilon over 4 squared. So we get that the transmission, the probability for reflection, okay, when the energy greatly exceeds the potential barrier, falls off as V over 16. Okay, and this formula might become handy for some of you if you're doing compound physics. All right. So this is a simple application of the probability current. And in your homework this week, okay, we asked you to using the probability current to investigate the difference between bound states and the scattering states. And there are some interesting properties in mathematics. Okay. So the next thing I'd like to talk about is moving on to the rest of chapter 4.
Oh wait.
Yeah.
Well, so the only thing that bothered me, if V was the same as E, so it would have been perfectly flat, but then the reflectance was 1. So
So what happens when this is perfectly flat? Right? So of course this is a mathematical. In real application, don't worry about this. So what happens when it's perfectly flat is actually you have sinusoidal wave here. But over here, you should have complex. You should have exponential decay, right? But that k, the kappa thing is 0. So you have a plane, you have a perfectly a constant over there. So it's a pathological case when they're exactly the same. This happens in electromagnetics as well. Right?
I guess I just might be misunderstanding the redrawing.
Oh, good.
Oh, never mind. Yeah. No, I figured what I was misunderstanding.
So guys, building on his question, this situation happens in electromagnetics as well, right? When you have an electromagnetic wave refracting at a boundary, right? What happens when you are exactly at the critical angle? You have total internal reflection, but what's left over here is a perfect plane wave. So it's also a pathological case, but this is just what comes out of the mathematics. You don't need to worry about this for real physical applications. No chance that is this barrier ever infinite, or is this ever exactly matched? Are there any questions?
Why we call it the probability curve?
Oh, okay. So you missed some lectures before. So we call it the probability current. Typically in electromagnetics, we call this the current of charge, right? Because we interpret rho as the distribution of charge, the charge density. But over here, the interpretation of the wave function is the probability based. And actually, I was just about to explain more on this fact. So give me a little time. Okay. So let's go back to that eigenfunction expansion we wrote down. Okay. So we said for any arbitrary function, and I'm going to refrain myself to one dimensions because things are easier to write. I can expand this onto the eigenfunctions at time t equals to 0. Okay. Now, and then the time evolution, of course, you just attach the time evolution factor for each of the eigenfunctions. So okay. So now let's actually explicitly write out the form of this probability density. So to do that, we need to take phi conjugate phi, okay, and that's given by phi. And I'm going to combine these things into a function of time. Okay, and this is in general a complex function of time, which is this fixed phase time. Okay, so then you see and then and now, if I was interested in the spatial integral of this quantity over here, so I'm integrating this over all space, all x. What happens here is these things are independent of x, so they come out of it. Okay, so now you have, we're going to use the orthogonality condition, orthonormality condition for the eigenfunction. So this term goes into delta n prime. Okay, this is the property of Hermitian function, Hermitian operation, and then this turns into so this delta function is going to remove, this product delta is going to remove one of the summation. So now, because we have interpreted this as the probability density function, we know that these things are normalized to 1 as well. Okay. So now these expansion coefficients, which are functions of time, can be given interpretation as classical probability. So what this means is, if I have some arbitrary wave function, and I make an expansion of the wave function in terms of the eigenfunctions of the Hamiltonian, and I allow it to evolve in time, then at a certain time, if I make a measurement of the energy of the particle with that wave function, then the probability, then these time-dependent expansion coefficients are going to give me the probability that I'll find the state in that energy. So this brings us to a point about the expectation value of operator. Okay. So in general, if I have some operator A, okay, I define its expectation value as one-dimensional. Of course, a generalization to multiple dimensions is quite simple. Okay? So this is what we mean by expectation value. And we're allowed to do this because of the probabilistic interpretation here. Okay? So now, the next thing to talk about, well, we can only afford to talk about this very briefly now because we lack the right formalism. It's called the measurement hypothesis. Okay. So if I have some, let's take a simple example. I have some potential, maybe the parabolic potential of a simple harmonic oscillator. Okay. And I'm in some state, let's say an eigenstate. Okay. And now I devise some kind of an experiment that measures the position of the particle. Okay. Now, what can I deduce from this probability from this wave function? Well, if I take the magnitude square of the wave function, which is going to look sharper, okay? So the magnitude square might look like this. Then the probability that I will find the particle at a certain position, okay, if I were to perform that measurement, is given by this probability magnitude square of the wave function. But now after the measurement, I should know that for certain that particle has a definite position because the measurement gives the particle a definite position. So we think about this as the wave function collapses onto a definite position. So maybe after the measurement, the wave function looks something like this. Okay. And the way you can think about this is what is this wave function? There is a really easy to use eigenstate on this picture, which is the position eigenstates. So the position eigenstates are given by delta x minus x prime. Okay. So these are position eigenstates. And by thinking about convolution, I know that this, not convolution, sorry. I know that this probability, that this wave function is nothing but, so phi of x is just the wave function of the particle expanded onto these position eigenstates. Right? So after a measurement, I collapse the wave function onto a position eigenstate. Okay. This is one example. Another example is, let's say we have an infinite square well. Okay. Infinite square well. And the particle is in some superposition of energy eigenstates. So the particle so the eigenfunction, the wave function may look like. Because the signs are complete, you can very well make a wave function that looks like this. So now I devise a measurement that measures the energy of the particle. Then I'm going to collapse the wave function. So after the measurement, the particle now has definite energy. So now I'm going to collapse the particle wave function onto a definite energy state. Let's say I find it to be in the ground state. Okay. So the analog between here and here tells you that this wave function thing, you really shouldn't think about it as a function of space. Because when you write down the wave function in the spatial representation, you're actually expanding it onto the coordinate eigenstates, coordinate eigen functions. You can very well, depending on what kind of, depending on the observable that you care about, you can very well expand your wave function in terms of energy eigenstates. And really, the expansion coefficient matters. You don't really need to worry about what the specific wave function look like. As long as you know the expansion coefficients, these things, then you know what are the probabilities. Okay? So in the next chapter, we're going to develop, based on these analogies, a uniform formalism that allows you to switch between bases very easily. Okay? and that is what's called the Dirac notation. Okay, and there's really no way to do quantum mechanics, real quantum mechanics, without Dirac notation. So that's where we're going. But what time is it now? So should I talk about the uncertainty principle?
Well, you should finish chapter 4. There are lots of things in chapter 4 that you skip. So why you want to go to chapter 5 now? It's kind of going out of order.
Okay.
Or,
So let me.
or maybe you can talk about 4.4. There's an uncertainty principle.
Okay, let me talk about the uncertainty principle. So throughout today's lecture, you have actually seen the necessity for uncertainty in quantum mechanics already. When we studied the free particles wave function, we said that to have a legitimate normalizable wave function for a free particle, you must allow for some uncertainty in the momentum. Otherwise, that's not a normalizable wave function. So let's specialize to a specific kind of wave packet. Okay. So this is a special case of the uncertainty principle. We're going to look at the uncertainty between position and momentum for a wave packet that has the specific form of a Gaussian wave packet.